Good morning. Today, by request, I'm going to do a video on compound interest. Now, a quote, probably apocryphal, attributed to Albert Einstein, says that compound interest is the most powerful force in the universe. Yeah. And Heinlein, Einstein? I have no idea. Heinlein says that $100 placed in a savings account at 7% interest, compounded quarterly for 200 years, will be worth over $100 million. By which time that will be worth nothing. So, some hyperbole on both sides, most likely. But what is compound interest and how is it calculated? Well, suppose you loan me $100 on the condition that at the end of a year I will pay you back not $100 but $107. That would be loaning me the money at interest. 7% interest to be exact. And calculate that for any interest by taking the amount that you loan me and then adding to that some amount times that little percent interest. Remember, a percent is per 100, so 7% is 7/100ths. That's the decimal way to write 7%. And we can just pull a p out of here. 1 plus 0.07. Now suppose at the end of that year, I say, well, I'm not quite ready to pay you back yet. I'll pay you back in another year. At again, 7% interest. Well, I'd promised to pay you back $107, not just $100. So what I'm really borrowing from you at the end of that year is $107. So I have to pay that 7%, not on $100, but on $107. So suppose this is your initial amount, P1. Suppose P0 is your initial amount. P1 is P0, 1 plus 0.07. Now, after the second year, taking the P1 amount and multiplying by this factor, 1.07. That's where compound interest gets its name. It's compounding. The money owed at the end of the previous period rolls over into the next year, and you pay interest on that instead of the initial amount, compounding it. All right, but this is P0 times 1 plus 0.07 times 1 plus 0.07. All right, and replace P1 with what it's equal to, which is equal to P01 plus 0.07 squared. And let's just generalize this all at one leap. The amount owed after some number of years t on some initial principal loaned at rate R, interest rate R, for t years is this formula. Take this factor per year, raise it to the number of years, multiply the principal by that. And that's your simple compound interest. Now, Heinlein said something about compounding quarterly. Well, how does that work? Well, 7% interest per year, compounded quarterly, is exactly the same as 7/4% interest per quarter. No difference. It's just that we want our variable to stay measured in years instead of quarters. All right, so the way to calculate that is 7/4% interest per quarter. Well, that's a rate divided by a number of compounding periods per year. That's what our rate per quarter is. So I'll call that R over N. R, the interest rate, in the number of compounding periods. Now, per quarter, 1 year has 4 quarters. If it's compounded monthly, 12 months per year. So to get a number of these small compounding periods, we multiply the number of years times the number of compounding periods per year. There. And that's your big workhorse formula for compound interest. Using this, we can actually check Heinlein's assertion about the $100 at 7% interest compounded quarterly for 2 years. 200 years. 200 years. Our principal is $100. Our rate is 7%, 0.07. Compounded quarterly, so divide that by 4. And in 200 years, there's 200 times 4 quarters. And I've run that through a calculator earlier, and I get 106545305, 2 commas, over $100 million, yes. And he asserts that in 200 years that will be worth nothing. Well, a lot can happen in 200 years. It reminds me of the story about the king who was going to put a man to death, and the man said, wait, don't put me to death yet. Give me a year and let me train your horse. I can train horses to talk. Imagine, you'd be the only king in the world with a talking horse. Just imagine the prestige. And the king said, well, why not? I'll give you my horse for 1 year. And after 1 year, if the horse doesn't talk, you die. Well, the man says a lot can happen in a year. You know, I could die, the king could die, the kingdom could be overthrown, or the horse could learn to talk. So, the profit in delay is the moral of that story, I guess. At any rate, and if you want to stop there, you know, more power to you. That's probably all you're going to need to know for your course, but what makes compound interest even remotely interesting mathematically is when we look at, say, the amount after time, well, let's give it a specific time, 10 years, for different numbers of compounding periods. Well, after 10 years with 1 compounding period, there's, say, this much money. 2 compounding periods, if you're compounding biannually, you get a little bit more money than if you just compounded once. 3 times you get a little bit more, 4 times you get a little bit more. The interesting mathematical question is, does this keep rising up towards infinity? The more and more compounding periods you have, the more and more money you get, or is there some level at which this never goes above? To answer that question, we need to take a limit. Specifically, we need to take the limit as n goes to infinity of that factor that we're multiplying the principal by here. And any factor, we're just going to raise that to the t. So let's just look at 1 plus r over n raised to the n. The limit as n goes to infinity of 1 plus r over n raised to the n. Well, that's the limit of. We can use Pascal's triangle, all right, and a little bit of combinatorics to write this out, all right, and I probably have another video on that. If I don't, I'll probably have one soon. So written out, this is 1 raised to the n plus r over n times 1 raised to the n minus 1, but you know, those are all 1s, times n choose 1, which is just n, so the n's will cancel, plus r squared over n squared, that that part squared, times n choose 2 plus r cubed over n cubed times n choose 3 plus, and so on, just like that. That's equal to the limit. What are these n choose 1s, 2s, 3s? What do they mean? Well, we know n choose 1. That's the number of ways to choose 1 out of a set of n objects. There's n ways. Those will cancel. 1 plus r plus. Now, n choose 2 is a bit of a different story. That's n factorial over n minus 2 factorial times 2 factorial. And that's times r squared over n squared. Apologize if my r's and n's start looking like each other. Plus n factorial, n minus 3 factorial, 3 factorial. I'm assuming you all know what factorials mean. For instance, 5 factorial is 5 times 4 times 3 times 2 times 1. You know, you multiply the numbers, the integers, all the way down. So factorial really only is defined on the integers. However, there is an extension of this concept of a factorial which works on any real number, any positive real number at least, called Euler's gamma function. So you might want to look that up if you're interested. All right, factorials. Now that I've shown you how they work, you should be able to see that n factorial divided by n minus 2 factorial is n times n minus 1. All right, and then we're left with a tivision of 2 factorial r squared over n squared plus, this is n minus n times n minus 1 times n minus 2 over 3 factorial over n cubed, r cubed over n cubed plus, and so on. All right, going to rewrite this. Going to swap these around and break up this fraction and do a bunch of steps at once, so try to keep up. N squared over n squared minus n over n squared. That's one of our factors here, incorporating this numerator and this denominator, so I'm sort of switching this around. R squared over 2 factorial plus, this is n cubed over n cubed plus 2/3 n squared over n cubed minus 2/3. I worked this out ahead of time. Don't worry if you're, just n cubed. Don't worry if you're not able to follow that, but I do invite you to check. R cubed over 3 factorial, and so on. Well, notice what happens in the limit. These are 1, and that'll happen all the way up. These, since we have a larger power of n, and n is going towards infinity, in the denominator, these all go to 0. So we can write down the limit. 1 plus r squared over 2 factorial, r cubed over 3 factorial, and so on, all the way up. Oops. Well, what is that? That's an infinite series. Is there any way of writing that more compactly? Yes, there is. There's a thing called the Taylor series. A Taylor series, any function of x can be written as itself evaluated, well, this is a Maclaurin series, itself evaluated at 0 plus its first derivative evaluated at 0 over 1 factorial, well, 0 factorial, times x plus its second derivative evaluated at 0 divided by 2 factorial times x squared plus, and so on, plus the nth derivative evaluated at 0 over n factorial x to the n plus, and again it just goes on. this function is equal to that infinite series. And the proof of that's very nice. Yeah. So let's apply this to e to the x. If you've had any calculus, you know that all the derivatives of e to the x are e to the x. And if you've had any algebra, you know that any number raised to the 0 power is 1. So this is very easy to evaluate. This is 1 plus x plus x squared over 2 factorial plus x cubed over 3 factorial plus, and so on and so forth. Exactly the same thing as here, except r's instead of x's. So this is equal to e to the r. And that's our factor. An amount in our investment after time t when we have r percent interest compounded continuously is the initial amount times this factor raised to the t. PERT. It's a nice little formula. Easy to remember, built-in mnemonic. But that's where it comes from, this formula for interest compounded continuously. All right, thank you for your attention. You have a good afternoon. Catch you on the next video.